Delighted to be here to share some observational results. We're going to go from theory land to the real universe for a bit. Work done with my current and former postdocs and collaborators, including Belinda Damian, who's here over there, who's a postdoc with Alex Scholes at St. Andrews and will be speaking tomorrow. So please pay attention to that. This whole project started about 20 years ago with Alex Scholes and myself embarking on a series of studies to study focusing on the lowest mass free-floating brown dwarfs and their disks. We were motivated by a few very basic questions, in particular, the question of how low in mass does the stellar IMF extend. Cora Music joined us a few years later, and the three of us, along with a number of others over about a decade, conducted the SONIC program, targeting 5 very nearby star-forming regions, primarily low-mass star-forming regions, and then added 2 more massive clusters that are farther away using the largest telescopes available on the ground and going as deep as one could do. Here we are. Here's a combined optical near-infrared image of NGC 1333 taken with Subaru Supreme Cam and Moirex instruments. This turned out to be one of our best targets. It's about 2 million-year-old nearby star-forming region, 300 parsecs away, relatively compact with low to modest extinction. In white circles, you see a number of previously known brown dwarfs that we recovered through imaging and spectroscopy is critical. And in yellow circles are a number of new discovered objects through our efforts. Just want to show that how deep can we go with the ground-based 8-meter class telescopes for these nearby regions, about 150 parsecs away, low extinction. You can get down to about 5 Jupiter masses, which is pretty much the limit for spectroscopy with these telescopes. And I want to emphasize how critical spectroscopy is. Here's an extreme case. One of the regions we targeted is Rho Ophiuchi with variable extinction, which makes things particularly difficult. You find lots and lots and lots, literally hundreds of objects with the right colors that people identify as brown dwarf or planetary mass candidates. And yet, when you take spectra of many, many, many of them, the few red crosses down there are the only ones that turned out to be low mass members of the cluster with low temperatures and the right surface gravity. So really, really important to pay attention to spectroscopy. Almost all of the rest are reddened background stars. So a spectroscopy is essential to identify the good from the bad, the interesting from the boring. And with an instrument like FMOS on Subaru, with just a few hours of telescope time, we could get about 50 spectra at a time. And that's the key to success. Multi-object spectroscopy in the near-infrared to confirm or reject these as members, low-mass members of the cluster. We try to extend these studies as low down in mass as possible for these nearby regions, looking for the lowest mass free-floating objects. Here's one of the lowest mass young objects that we confirmed with spectroscopy right at the top. You can see it's a crappy spectrum. You don't get much, but you get enough to see the very sharp triangular shape because of water absorption on either side of that peak, showing a characteristic sign of a very low mass young object. So that peak gets more pronounced as you go to lower temperatures, which is exactly what we need to probe into the planetary mass regime. We also did a series of studies of disks of young planetary mass objects in these regions. Here's just one where we stacked 70 Spitzer IRAC images at 3.6 and 4.5 microns. And added together, these images go about 2.3 magnitudes deeper than single epoch frames and cover about 50 brown dwarfs in this particular region in NGC 1333. And out of the 50 brown dwarfs, about 15 have spectral types of M9 or later, which is approximately the boundary for the planetary mass regime. Here's just a plot showing IRAC1 and IRAC2 colors against K-band colors. About 5 out of the 12 planetary mass objects on this plot show definitive evidence of infrared excess in one or both bands, implying a disk fraction of about 42%, albeit with large statistical uncertainty given the small sample size. Then comes the James Webb Space Telescope, long awaited, allowing us to go much deeper and fainter in these young star-forming regions. I've been a member of, I'm ashamed to say, I'm embarrassed to say, I've been a member of the NIRISS instrument team for 21 years. I know I look young. And thanks to that participation in the science team of the NIRISS instrument, which is the Canadian-led, the smallest of the 4 science instruments on Webb, we were able to secure 20 hours of guaranteed time to do an ultra-deep survey of NGC 1333, go way deeper than we could from the ground. In particular, in the wide field slitless spectroscopy mode, it's a terrific instrument for targeting the lowest mass objects, particularly in a compact young cluster. So Alex, Cora, and I planned this potential GTO program back in 2014. We had hoped to get 9 pointings. Eventually, we got 7. This is some of the early work we did planning for it. I won't go into details. What was really exciting, as I said, with JWST is the prospect of reaching lower masses than we could from the ground. In particular, we could investigate what's called the opacity limit for fragmentation for the first time observationally, which is something we couldn't really do from the ground. There are just 2 of the papers from 1976 and 77 that calculated this opacity limit, and you can see that one of the papers I've highlighted there already estimated the opacity limit to be about 7 times the mass of Jupiter. So we know this is somewhere between 5 to 8 Jupiter masses, and that we thought we could definitely get down to with JWST. So 10 years after our initial planning, here's what we got: a mosaic of 7 fields in 2 colors, 150 and 200. The images are stunning. Here's the mosaic of NGC 1333. But what's special, as I said, is that with the NIRSS instrument, we could get spectra of 600 plus objects in these fields with K magnitudes brighter than 20.5. We were able to recover 19 of the previously known brown dwarfs. You can see I'm actually quite stunned by how well our data from Subaru from 13 years ago match the data from JWST, given both sets of spectra are kind of crappy, to be honest. And yet, they land right on top of each other with no fixing. This is amazing. These are 6 of them. And out of the 600 plus objects for which we had spectra, we identified 6 new objects that turned out to have L spectral types, which corresponded to masses between about 5 to 15 times that of Jupiter at the age of this cluster. Here's an example of one of those. You can see some of the steps of our reduction. Here's the 2 images. Here's the template model fitting. I won't go through all of the details. Right at the top, you can see the spectral fit. Not the best signal to noise, I admit, but good enough for identification purposes. Here's another one. One of the 6 newly identified objects at 5 Jupiter masses is the lowest mass object known to harbor a disk excess from Spitzer. We also looked for binaries with separations less than an arcsecond, and we found 6 of them in our sample. And one of them is particularly interesting, NN10. This was a known brown dwarf, previously known brown dwarf, and we found a planetary mass companion to it about 160 AU away. It took some work, but Adam Langeveld, my postdoc, was able to actually extract spectra for each of the 2 components separately. This system certainly deserves further study. What I find most interesting in some ways is what we didn't find. We did not find any objects with spectra of T-type. So we did not find characteristic T-dwarf type spectra for masses below about 4 times the mass of Jupiter, despite the fact that our survey, we believe, very well reached below that. So the fact that we don't find any T-dwarfs, we think, is interesting. As I said, theory predicts an opacity limit for fragmentation, somewhere between 3 to 8 times the mass of Jupiter. And the question is, are we now kind of scratching the bottom of the IMF? Are we really reaching the lowest mass objects that form like stars? I think the next speaker will contradict me a little bit by a Jupiter mass or 2. But I do think that one really wants to have proper spectroscopic characterization to be sure of the lowest mass, faintest objects we are studying. I'm going to switch gears for a second. Very separately, through a GEO program that we submitted to JWST, we targeted 8 planetary mass objects in a few different regions nearby that showed infrared excess from the ground, and we targeted them for 1 to 13 micron spectroscopy with NIRSpec and with MIRI, a combination. And Belinda will talk more about this sample tomorrow. So I'm going to not cover it, except I want to tell you about one particular object, the one that's circled over there, Chameleon 1107 minus 7626. This turned out to be incredibly exciting and interesting. Belinda will tell you what Laura Flagg, my other postdoc, and until recently, and Belinda herself, 2 studies that they worked on the sample, including on this particular object. But Victor Amandro-Sabad did some follow-up spectroscopy for us with the XSHOOTER on the VLT for the last several months. We were trying to monitor these objects with accretion disks to see what's going on, to characterize them better. And what we found was incredibly exciting. He noticed a huge jump in the strength and shape of the accretion-related lines in June, this last June, compared to the spectra we had taken in April and May, just a couple of months earlier. This is the first time that an accretion burst in a free-floating planetary mass object has been captured in real time. This has been really a wonderful, exciting effort. So we've continued to monitor this object with the VLT over the summer, and we also got director's discretionary time on JWST to observe it with NIRSpec and MIRI in August. Here you can see, I don't think I can use the pointer very well, on the right, you can see the Partian gamma line, there's the hydrogen H alpha line. We have a total of 8 epochs color-coded here that clearly show the evolution of the accretion burst. This is a cool animation that ESO did for us, showing what's going on. We think here we're looking at the backside of an accretion column from the inner edge of the disk onto the central object. The absorption, because you're looking on the backside, explains the absorption in the middle of the H alpha line, the double-peaked shape of the H alpha line. So usually in astronomy, we talk about time scales of millions of years or billions of years, maybe tens of thousands of years in some cases. But here we were witnessing something that was changing over just a few weeks. This made some news, including in the Wall Street Journal. I imagine Wall Street bankers reading about this curiosity and being amused. You got to get their attention when you can, right? Here's the time evolution plot of the accretion-related features. You can see the H alpha in blue, the Partian gamma in orange, and an average of all the traces that were available to us in the black diamonds. In short, we saw an 8-fold increase between the spring and summer in the accretion rate, the inferred accretion rates of these objects. Just a couple of days ago, we were awarded director's discretionary time with Gemini Ghost spectrograph because we want to see if this burst is continuing still or has it ended. At the last epoch of observations we had, which was in late August, still showed it in the high accretion phase. What was also interesting was that the JWST spectra we got at lower resolution, but very high signal to noise with NIRSpec Prism and MIRI LRS revealed changes also to the spectral energy distribution. Specifically, we saw the appearance of a water vapor feature and changes to the hydrocarbon and silicate features that we had seen before during the accretion phase, high accretion phase compared to the lower accretion phase. So it's been quite an exciting ride. So again, here's an attempted early preliminary set of answers to the basic questions that that set us on this journey. We think that the low mass IMF, we can see it extends to at least 5 Jupiter masses. Whether it extends any further, we would love to be able to do deeper studies of multiple regions to do, and other groups are doing that too. In our case, where we are confident we don't see any T-dwarfs in this particular region in the position in the survey region anyway. And how common are PMOs relative to stars? On the order of 10%, down to about 5 Jupiter masses. That's where we're not finding. We're not finding 1-to-1. We're not finding hundreds of them per star. We're finding about 10% of them per star. And these characteristics continue to be interesting for their own sake, both the objects themselves. Again, Belinda will talk about spectroscopy, not just of the disks, but also the atmospheres and atmospheric features of a couple of these objects that are really interesting in comparing to both exoplanets and young stars. And this accretion burst was a wonderful, somewhat fortunate find on our part. So I'll end there and answer any questions. And our chair didn't get to have her fun.
It was about to go off. Perfect timing. Question. Oh,
why you don't have T-dwarfs?
Why don't we have T-dwarfs? Because we don't think they are produced as commonly, given the entire cluster is a couple of hundred stars. So if you only have a few percent, right? So we can put an upper limit that it's on how frequent they are relative to the number of stars, right? So it's not that they exist, there's zero, but not enough to be found in a survey of a cluster with just a couple of hundred stars. That's my best guess.
Can I just follow up and say, what's the latest type object that you did find?
I think it was a L5 or L5, L4 or 5.
So no L8s, because the T's tend to start, they still look like the L's for a while when they're young.
No L8s.
Right. So not just no T's, it's no late type L's. Oh, I did. I'm sorry, Matthew.
But remember, with just like half a dozen L's, the statistics are such that, there could well be a few, right? But the point is that they're not being produced as free-floating objects by, large numbers relative to the number of stars.
Other questions?
It'd be great to do this kind of study for a more massive cluster with, thousands of stars. The problem is that the nearest ones are kiloparsecs away, not hundreds of parsecs away or 300 parsecs away. So again,
do you have a mass function for your objects? And is there any signature of brown dwarf desert like fall and the numbers? No.
Not in the same way that there is for companions, but the power law function continues. What we don't see is a second bump.
Right. Okay.
Yeah.
But I mean that fall, the driest part in the desert, is it like 30, 40 Jupiter masses for companions? So presumably you should see it if it was in your data, right?
If there was a desert of like 30, 40 Jupiter mass objects?
Yeah, at masses, yeah.
No.
That's
so
the question.
the power law continues sort of unbroken.
Right. Okay.
Down to about this, right?
Okay.
Yeah. But if you are ejecting lots of 5, 10 Jupiter mass objects, you should maybe see a second bump, and we don't see that. Yeah.
Question up here.
So you mentioned the system with the brown dwarfs with proto-mass companions. How does the number compare with just the number of brown dwarfs?
Brown dwarfs with planetary mass companions.
Yes.
So we found one. It's consistent with what you would find, for example, I mean, when you look at some of the nearest regions, TW Hydro Association comes to mind. When you have one, maybe two, it's consistent within those low number statistics, if that's what you're asking. Are you asking, should we expect to see many more planetary mass companions around brown dwarfs or not? Or are you asking?
Yeah, I'm wondering about the binaries compared to single brown dwarf number. What's the ratio?
Oh, okay, I see. You're asking how many binary brown dwarfs are there? I think we found 6 within an arc-second separation out of a few dozen total brown dwarfs. Okay, thank you.
All right, thank you, Ray J.